So how do we calculate an F-statistic? In this class, we're going to keep it relatively simple. And I'm just going to quickly flash through some notes that I have from previous semesters where I actually went through all the calculations that you would need to get there. So on these notes, you can see there's kind of a whole lot going on. So you start with something called the sum of squares within groups. You go through calculations for each group, you add them together, you divide by some other stuff, and that gives you something called the mean square within groups. For between groups, you've got a different formula, you do a whole bunch of stuff, you divide by some more stuff, and then you get something called the mean square between groups. In this class, I am not going to have you go through all of these steps. This is another thing that I think is not really worth your time in learning how to do, since computers will do all of this for you. But I do want you to know what the mean squares within groups and mean squares between groups refer to. And so I'm going to write here MS between, and that refers to the mean square between groups. And I'm just going to say this is a measure of between group variation. So conceptually, talking about the mean square between groups, we're talking about how far apart the different group means are from each other. So we have a high MS between groups in this scenario, and we have a high MS between groups in this scenario, where each of our groups are spread apart pretty far from each other. Our mean square within groups refers to how much within group variation we have. So I'll say this is a measure of within group variation. And so within group variation refers to the amount of variation that there is within each group. So you have a lot of within group variation in this example where, again, all our scores are pretty spread out from each other. And you have a lot of within group variation in this example where, again, all the scores for each particular group we're looking at are spread out from each other. So our curlicues are far away from each other, our lines are far away from each other, and so on. So going back to the idea of the mean square between groups and the mean square within groups, we're going to say that these are measures of variability that are calculated in ways that we're not going to go through here, that describe the extent to which there is variation between groups and variation within groups. So the larger a number you have for this one, the more between group variation you have. The larger a number you have for this one, the more within group variation you'll have. Your F statistic is simply going to be given by this equation. It's your mean square between value divided by your mean square within value. So there'll be some number for this one, there'll be some number for this one, and you divide them together to get your F statistic. So I'll say this is an F statistic, and this is the test statistic for analysis of variance. So when I go through the steps for analysis of variance, I'll go through all of this with more examples. But there are a couple of things I want to note about the F statistic before I do. And I'm actually going to come back over to the sheet here. Your F statistic is highest in a scenario that looks like this. So you have a lot of between group variation and relatively little within group variation. So you have a high number in your numerator and a low number in your denominator. That gives you a high F statistic, and that describes this scenario. If you're in either of these scenarios, where you either have a lot of between group variation and within group variation, or low between group variation and low within group variation, you'll end up with sort of a medium or moderate sized F statistic. So it's going to be a big number in this scenario. It's going to be not a huge number, but not a tiny number in this scenario. In our last scenario, though, we have a big number in our denominator, a small number in our numerator, and because of how division works, this means you end up with a small F statistic. So our final scenario here is going to be described by a small F statistic. And what all of this means is that once you calculate the F statistic, you get some information about which kind of scenario best describes your samples. So if you have a high F statistic, you know that your samples look more like this, and you have a good reason to believe that the samples truly are drawn from populations with different means. Because it's unlikely that you'd end up with a bunch of cases clustered on one side, a bunch of cases clustered on another side, and a bunch of cases clustered somewhere else, just by chance. If really everybody had exactly the same attitudes about death penalty support here. If you have a very small F statistic, you don't have a lot of good evidence that these populations are distinct. Because if each group had the same mean, it seems pretty likely that you'd end up with a distribution like this just by chance, where everything's kind of overlapping each other and your samples aren't really distinct from each other. So the bigger your F statistic is, the more evidence you have that you have populations with means that are distinct from each other. The smaller your F statistic is, the less evidence you have that you have populations that are distinct from each other. Because of this, we can use the F statistic to conduct a hypothesis test. And here we're going to be using something called an F distribution. And an F distribution looks something like this. It's a sampling distribution for different possible F statistics that you could get. So if you take a bunch of samples, calculate an F statistic, it tells you the probability that your F statistic is going to be really low or really high. And this is a standardized distribution, so it's the same each time. And depending on where your sample falls, you can calculate a p-value. And the p-value is the probability of obtaining an F statistic that is as large or larger than your F statistic. And in this case, you can see this is sort of a skewed distribution here. We don't have a mean drawn through the center. And this is because F statistics can't be any smaller than 0. So here we're starting with 0, and then we just get larger and larger from there. So how the analysis of variance test works is that you take a couple of samples, you compute the mean squares between and the mean squares within that tell you how different the samples are from each other and how different observations are within each sample. You use that to calculate an F statistic, and then you plot that F statistic on your F distribution. If your F statistic is on the far end of the distribution, it means that it's unlikely to have occurred if all the populations had the same means. And so to clarify here, this is a sampling distribution that shows us what we would expect if the null hypothesis was true. And so this follows the general logic of hypothesis testing, where we are plotting our sample on a sampling distribution that describes the world if we assume the null hypothesis is true. The only difference here is that instead of looking at a t-distribution, we're now looking at this f-distribution, and instead of plotting a t-statistic, we're plotting an f-statistic. But the bigger your f-statistic is, the more evidence we have that the groups are different from each other. And our f-statistic produces a p-value, and then we'll use that p-value like we would in any other hypothesis test. So now I've gone through the main concepts that we need for doing this analysis of variance test. The next thing I'm going to do is talk through the actual steps for doing the test and go through an example that involves some actual numbers. So I'm going to hop back over to the slides, talk about the steps for the test, and then come back into the document camera and go through an example.